review it, and then we will jump to the one which you're talking about is materials. Okay. The the in initial time I told you there is a model which actually we will be dealing all the time, and that model is called Rutherford model, right? In Rutherford model, how actually we reach to that model, that's what the point is actually. Because I have seen that question comes in examination, so better discuss it, right? Now, how to reach to this model and why we actually reach to this model, what is the reason for that? Initially, when scientists start working on that, they didn't have a concept of this nucleus or something or whatever it is. What they're thinking at that time was that full of this area which is inside a nucleus is made of positive charges, and there are very few electrons somewhere around the around the protons. But the scientist who actually did that, his name was Rutherford. What he did, he bombarded alpha particles onto this nucleus, and the results which came in are very surprising. Now, what are the results? Check it out. This is alpha particle. Most of the alpha particle which are actually bombarded on the atom, they passed straight down. Very few reflected back, and some reflected at a very certain angle or deflected. The question is why they actually pass through. What could be the reason? What do you think? Yes, Manu, what do you
The
think?
nucleus is mostly empty space.
So basically, the first important part, which actually he concluded from the results, is that most of the atomic part or most of the atom from inside is hollow, or you can say is empty, right? So that's the first point we have it. The most of the atom is hollow. Second thing is very few alpha particles are also deflected with a very small angle like that. You can see here, which shows that definitely there is a very narrow or very small positive charges which are actually present somewhere in the middle of the atom, and they called it atom. So actually these alpha particles are deflected by that, and that's the reason the angle is very small. So another part we found out that a nucleus is somewhere inside the atom, which is a very small part. We have it, and some is reflected back. It means that definitely the alpha particles are the positive ones. So it means that basically protons are right there in the center. That is the reason why it is reflected back. So actually the results which actually achieved from here leads to a new model or thinking of a new model called Rutherford atomic model, right? So Rutherford atomic model is the model which we studied, and on the basis of that, there will be new and different models came in. So I want you to write that because I've seen that question, what is the path of alpha particles? So you have to just write it down. So evidence for the structure of atom was discovered by Ernest Rutherford in the beginning of 20th century from the study of alpha particle scattering. This structure is commonly referred to as a nuclear model of the atom. The experiment setup consists of alpha particles fired at this thin gold foil and detector on the other side to detect how many alpha particles deflected at a different angles. I want you to just write it down. This is very important actually. Put a heading nuclear model of atom and on top put alpha particle sketch. Draw the diagram as well. I want you to just draw that diagram as a result, and then we will write upon this. Okay. These are the results he just found out. We will discuss them one by one. Let's draw that. Now the results are here. See, the first result of the experiments are summarized here. The majority of the alpha particles went straight through the gold foil without deflection, right? So what does it mean? But it suggests that atom is mainly empty spaced. Secondly, alpha particles deflected through a small angle less than 10 degrees. It means that this suggests that positive nucleus at the center, since two positive charges would repel. Very simple. Only small number of alpha particles deflected straight back at an angle greater than 90 degrees. This suggests that nucleus is extremely small, and this is where the mass and the charge of atom is concentrated And it was therefore concluded that atom consists of a small, dense, positively charged nucleus. So these are the three results on the basis of that we are actually talking about.
Sir, I'm done.
Okay, now what was a model before quickly? That was a model. We call that plum pudding model. Now, what was plum pudding model? Since atoms were known to be neutral, the negative electrons were thought to be on a positive sphere of a charge. Plum pudding model before the nucleus was theorized. It means that that is your positive, you can say, diameter or something of charges around which your electrons are revolving around in different space. That was the thinking actually. Now it's known that the negative electrons are orbiting the nucleus. Collectively, these make up the atoms. Okay. So basically, that was a model before, and the atom is around 100 times larger than the nucleus. That's what the thinking was. So that was a small thinking. Now, quickly, the question is, where is it? In alpha particle scattering, a student setup, whatever, which of the following graph best represent the variation of n with a theta to 90 degree? That's nothing but, SI. Okay, now quickly what the thermionic emission is. There we go. Okay, now thermionic emission, as the name suggests, when you heat up something, electrons are actually, we have, no, this is actually photoelectric effect that will, inshallah, in the second paper, once we come to that, we will find out. Okay, now another one, let me just see that. This is not a part of us, anyway. Okay, this is sorted, done. Now let's start with our chapter, which we were saying last time. Okay, in this chapter, when you talk about a matter, what is the first thing come in your mind, Maru? Every matter has some properties. On the basis of that property, that matter would be noun, or you can find out, yes, that is what the matter is. Now, what are the properties of that matter? Okay. Now, properties are written over here. I'll show it to you. There are so many properties you have. It like mass, we know that a quantity that is present in a body. We have a volume, we have a density. Then there is a thing called Young modulus, which we will be talking later on. Then we have a stress, strain, elasticity, ductility, hardness, softness, brittleness, toughness, strengthness. So these are the qualities on the basis of that we can differentiate different type of materials, which we will be discussing as we will move on. The special part is on the basis of that when you discuss it, what is meant by density when you say that? Density is simple mass per unit volume. If the density is more, what do you mean by that? Yes, Manu. When I say density is more, what do you think? What does it mean?
The particles are tightly placed together.
So it means more particles are there in a small volume. You can say like that. So it's tightly packed, and more particles are there in a very small place. It means that it's heavy loaded particles at a one special space. It's same if you want to understand that concept, you can say that in Pakistan, in India, for example, at 1 kilometer area, 1 kilometer square area or 1 meter square area, there are 300 people living. In Saudi Arabia, there are two people living in 1 kilometer area. So where is the population more dense? In India, right? So it's same like that. If more denser means more molecules per unit area. Less denser means less molecule per unit area. So this is one of the property of the matter. Okay. Now what I am interested in is, check this out. Can you do that? Density of a copper at a room temperature is about 9,000 kilogram per meter cube. Calculate the mass per meter of a copper wire that is 1 millimeter in the diameter. What would be the mass of 2.5 meters of this wire? How to solve that? You have to find out the mass per unit length or mass per unit meter. So what to do in this? You have to find out mass per unit meter, right? And they have given you the diameter. Find out the radius, and you know that a cross sectional area is a circle. So find out an area and multiply it with 9,000. That's it. You will find out kilogram per meter. Like I
I
can
have
see.
0.00225.
Okay. And what about the second part? How do you solve it now? You have to find out the volume by using 1 millimeter and then multiply 9,000 by the volume of the wire. And it will give you simple the length, I mean, the mass of the quantity, because mass is density is equal to mass per unit volume. Find out the volume and multiply it with the density. You already found out the area, right? So area multiplied by the
Yeah,
length.
it's 0.0176.
Let's see. Is that the one? Okay, let's move on now. Now let's jump to the next small topic. Now, if you really want to write it down, you can, but I don't want you to write it just write one line, because these are important. So I have to explain these small quality like stiffness and ductility and this all. So if you want to write it down, up to you, but I will quickly go through that, what exactly it is. Firstly thing is called as stiffness. So if this stiffness is a resistance of a material to being bent, whether elastically or plastically. Now, before you understand this stiffness, ductility, I have to tell you this elastic, plastic, and all this. So let's quickly see what exactly this elastic and this plastic thing is. For that one, we have to go through certain rules here, and let's see what exactly it is. There is a graph which I have to tell you, and that graph means very much to me and very much to you as well. And what that graph is, let me just see. Yeah, this is the graph. Now, the first thing or first law which actually makes us understand or to explain something is called as Hooke's law. Now, what exactly is Hooke's law? That's what we have to explain here. Let me just see. Yeah, it's there. That's what I'm saying. This is the graph I'm talking about. Before we go into the detail of that, what exactly is what, let's explain this stress. What is meant by stress, Manu? When you say stress, it means pressure, remember that. And pressure is equal to force per unit area. So when you apply a force per unit area, you're talking about a stress here. So put a heading stress, first of all, and write it down. Stress is defined as force per unit cross-sectional area. Force per unit cross-sectional area. And the formula is written here, that rho means stress. Sometimes stress is defined as this symbol. So this is written as stress. The unit is Newton per meter square or Pascal. Okay. Now the second thing is called as a strain. In general, what does it mean? For example, let's suppose you got a spring here. You pull it. What will happen? That will be expanded or extended, whatever. So that particular height will be considered as a equilibrium state. Equilibrium state means a state at which it's not extended. And the second one is your extended state where you actually expand it. Okay. If I ask you how much that particular spring is expanded, how do you find out? Let's suppose the initial length was L naught and the final length after applying the force become L1. So what is the extension? How can you find out the extension? E is equal to L1 minus L2. Am I right? Hello.
Yes.
So basically, when you apply more force, the thing will be more expanded. Am I right?
Yes.
So basically, how do you explain a strain? Strain means extension divided by the original length. How much an object will expanded or extended per unit the original length. If this value is increased or reduced or mild, that tells you different type of objects. What will be the unit for that? There is no unit because extension and original length has a same units. So I want you to put a heading strain now. Strain is defined as strain is defined as extension per unit original length. Extension per unit original length. Let continue in the next line. Let L naught is the length of a spring. Let L naught be the length of a spring. After applying a force, the length of a spring is expanded and the new length is L1. And the new length is L1. So the extension in the spring, can be given by E is equal to L1 minus L naught. So the strain, the symbol for the strain is this epsilon. So the strain can be defined as E is equal to extension upon the original length. Just write one more line. It has no unit as it is the ratio between the same quantities. As it is the ratio between the same quantities. Okay, now few more things. Let's put a heading Hooke's law. Hooke's law. To explain that, we have to explain the Hooke's law first. And let's quickly see what the Hooke's law is saying. Manur, what is Hooke's law, by the way? What comes in your mind? Yes. How to define it?
Well, I know the equation.
Okay, let's do that. Okay. So basically, when you express or when you say Hooke's law is saying that when you apply the force, as the force is bigger, the extension in the spring or extension in the device will be bigger. So you can say force is directly proportional to the extension in the spring. So When you remove that directly proportional sign, you will put a constant, I mean, you will put a equal to sign and a constant k will be multiplied. So your equation is F is equal to KE. And sometime you will find an equation like this, or sometime you will find the equation like this. So don't be confused with the symbol. Equation will be F is equal to K extension. So I want you to put a heading Hooke's law. And what Hooke's law is saying, let's write it down. Hooke's law is saying force applied on a spring is directly proportional to the extension in the spring, to the extension in the spring, provided, either you write provided or you can say within the elastic limit, so basically what exactly it is, force applied is directly proportional to the extension in the spring within the elastic limit. Now, what does it mean actually? If you see the graph between a force and an extension, you can see that from point O to point P, you will have a straight line. It means that till this point to this point, you will have a elastic limit. After that, if you can see the graph here, that graph becomes a curve. It's same like a resistance and current graph. It means that at this point, now force and extension will no longer be directly proportional. So at that point, then we have to specify some other way. We have to do that. But this graph shows us that between O and P, you will have a direct relationship. You apply the force and X will be extended or there will be extension. Okay. So I want you to draw that diagram and write till here. Now, this was the old stuff. I mean, we have just noted that and everything. Now, finding the K value will be very easy. You move the rest of the thing on the other side and it will be F upon E and you will get the K value. Or if you draw a graph and you will find the gradient of this graph between F and E, you will find the K value in that. I am much interested in that circuit because this is actually our main stuff. Now, if you check this out, you can see here there is a series combination of the spring and there is a parallel combination of a spring. You tell me one thing, in which combination you will find more tension, in series or in parallel? So my point is, you tell me which particular circuit or which particular spring combination you will find more tension, in series or in parallel. What's your point?
In the series?
In a series. The reason is very simple. When it is stretched, both the springs will be stretched. The first one as well as the second one. If both got the same constant, then actually there will be a tension in both of them. So technically speaking, here the tension will be added. So technically speaking, this is the additional circuit. You will add the tension here. While here, the tension will be divided in the two circuits. Here the tension become half, here the tension become half. So actually this is T is equal to W by 2 and W by 2. So this is what we called as combination of the spring. I want you to put a heading combination of a string and just draw them, please. Also write this formula. So this is for the, that series combination. Okay, now another small thing quickly, Young modulus and very small thing, simple harmonic motion. To find out the time period, the time this is all actually about the old stuff in IGCSE. But remember that if you need to find out the time period, the formula is that. And what exactly is the formula? It is the formula. I don't think so. This is in our course, I believe. So if it's there, let me know, but I don't think so it is because it's just there. So I had to. But anyway, what is Young modulus, Manu, exactly? Young modulus is basically the division of stress and strain. When you divide stress by strain, you got a constant called, not a constant, you got a constant called Young modulus. And remember that this is the property of a material. that how much strain it will have by the application of certain stress. So what is it actually Young modulus? Young modulus means stress over the strain. Very simple. There is a formula for this. I want you to put a heading Young modulus and then write it down. Young modulus is a property of a matter. Young modulus is a property of a matter of a material. It is the ratio between tensile stress, tensile strain. It is the ratio between tensile stress over tensile strain. Okay. Now let's quickly see what exactly it means. You mean stress divided by strain. Stress in generally we know that. What do you mean by strain? I mean not strain. What do you mean by tensile? Tensile means when you're talking about force per unit area. Okay. And extension, especially when you talk about tensile strain, it means that you're talking about a very small change in the length. Remember that there can be a change in the area and change in the volume as well. But when especially you're talking about change in the length, you will talk about tensile strain. Now let's check it out. Stress is equal to, if I say P, for example, if I say rho, it is F upon A. And strain will be equal to what? It will be change in length per unit original length, right? Now place the values in the formula, so it will be F upon A over E upon L. Now it means that F upon A multiplied by L naught upon E, like this. So now if you actually found this formula, you will see that FL divided by AE. Now let's put the values, I mean, put the units in that. F means force, which is Newton. L is the meter. Area is meter square. And E is also meter. So meter and meter cancel. It means that E, which is Young modulus, has a unit Newton per meter square. So unit of Young modulus is newtons per meter square. Manur, any problem in this, beta?
No, sir.
I want you to quickly write it. Also, this is very, very important. Young modulus is a measure of stiffness of a material. Okay. Okay. Once you finish it, I want you to solve this numerical. Mild steel has a Young modulus E is equal to 20 into 10 raised to the power 10 Newton per meter square. A steel wire of length 1 meter has a cross-sectional area of 1.0 millimeter square. Find the extension if a force of 100 Newton is applied to the wire. The formula is the same, which is right there written. You have to just use the formula. But one thing is important in that you need to have all the units in one system. Yes, Manur, any problem in solving this numerical?
No, sir.
Formula is there. Only thing which I can see is 1 millimeter square. You have to convert that millimeter square into meter square first. Then you will be able to solve that, right? Okay, let's see that. Let's write the data
I
first. Yeah, you have
I
done?
got 20 times 10 to the power of 7.
Okay, and what will be the unit for that? Extension must be
New
meters.
it's meters, yeah.
Here the answer is 0.5 millimeter. Is that the answer? 5 into 10 to the power minus 4.
Oh, I made a mistake doing the millimeter squared.
Okay, you keep it in millimeter square. But you have to convert it because all the other units are in meters. So either you convert them into millimeter or either you convert this millimeter into meters. Now I'll let you know because this is what the most of the students have having a problem. 1 meter is equal to how many millimeters? 1000.
1,000.
1000 millimeter. Okay. And when you say 1 meter square is equal to, it means 1000 multiplied by 1000 millimeters. So basically 1 millimeter square will be equal to 10 raised to the power minus 6 meter square. So you have to multiply your one, where is it? Uh, where is it gone? Okay. You have to multiply this one with 10 raised to the power minus 6. So basically that will be equal to 10 raised to the power minus 6 meters square. Now rest is very simple. The formula is E is equal to FL divided by AE. Force is how much? 100. Length is how much? 1. Area is how much? 10 raised to the power minus 6 and multiply by Newton. I mean, not Newton, E, which is equal to 20 into 10 raised to the power 10. If you solve it, you will get 0. Not 0 point, you will get actually 5 into 10 raised to the power minus 4. And afterwards, you can convert it into millimeter by dividing it to 1000. Or by it's I mean, it's a meter given, so you have to convert it into that by multiplied by 1000. So when you do that, you will get 0.5 millimeter. One more thing, and then we will finish the lesson for today. Whenever you have a graph between a force and extension, the gradient of a graph means, whenever you find the gradient of a graph, the gradient of a graph means Newton per meter. So this is what the gradient of the graph is. So I want you to quickly draw this graph, and let's write something about this. And remember that this line means it's a line of a best fit. It's not the actual line. The points are there, up and down. So they have actually drawn a line of best fit there to get the exact results for that. Write few lines there. Just write E is equal to FL over AE, and then write down the gradient of force versus extension graph. The gradient of force versus extension graph is Newton per meter, or force per unit length, force per unit length, or force per unit extension, force per unit extension. Yes, Manur, did you copy?
Yes, sir.
Okay. Manur, I believe I'm not that fast. Will that be fine? Speed is fast and not that slow, but not that slow as well. You understand everything?
Yes.
Any questions?
No, sir.
Good. So we have done just young modulus, Hooke's law, and all the things. Inshallah, tomorrow we will continue from here, and then we will go to now next. Our next step will be stress and strain graph. How do we define it, and what are the, you can say, stops, or what are the points which we have to discuss very much. Once we go through all the theory, then we will jump to the numerical part of it. The qualities or material properties will be discussed over here in this session now, which is tomorrow and day after tomorrow, hopefully. Right? Okay, then see you tomorrow, inshallah.